So good morning everyone. So it's an honor for me to present a part of my work in front of you today. It's developed in our lab and it's an innovative process to achieve a stable green and red emitting phosphor for cost-effective optoelectronic application. So myself, SUBHAJIT Datta, I am a PhD scholar from Sungkyunkwan University, South Korea. And here you can see a drone view image of our university, and our university works in collaboration with Samsung Electronics, and it has a very good infrastructure for research and innovation. So before moving deep into my presentation, here is a brief introduction about myself. I am SUBHAJIT Datta and I am a PhD scholar registered under the School of Advanced Material Science and Engineering. So my research journey started in 2010 when I joined in BTech as an electronics student, and after that I did my graduation in nanotechnology in 2014 to 2016. After that I served 4 years as a research assistant in CSIR National Aeronautics Laboratory in India, and finally I joined in 2021 here as a PhD scholar in Material Science Department. So my advisor professor is Professor De Hoi Yun, and he has two different team. So one team works on energy material, where they synthesis nanomaterial or MOF for OER and HER reaction, and the second team is the luminescent team, where we synthesis the perovskite or the phosphor or quantum dots for different LED and display applications. Since today my topic is on phosphor, so let's know what phosphor is. As coined by Dr. Rudiger Pescotta, phosphor are the light-emitting substances which are widely used in various kind of luminescence or display devices. So, in general word, like the phosphors are the material that emit light under certain conditions. So if we look into its working principle, so when high energy radiation comes and fall onto this phosphor materials, their carriers are generated and goes to the excited state. So after a certain period of non-radiated transition, these excited carriers again jump back from the excited state to the ground state with some fluorescence, and this fluorescence are in the visible range, which we can see as emission, visible emission. If we look into the phosphors today, like phosphors are used in almost all sort of lighting, from our car lighting to our home lighting. So here are some phosphor materials that are being widely developed and used at present. So as I told, it has a wide range of applications, starting from road marking to bioimaging to solar cell, photocatalyst, even in some safety and toy decoration, some extreme condition applications, and also in LEDs. However, among these applications, some are well established, like the toy decoration and the safety markers. Some are under progress, like the extreme condition applications or LED or even road marking and bioimaging, and some are still very much challenging, which requires a good research to overcome those challenges, like in the case of photocatalyst and in case of solar cells. Moving on towards the application of perovskite as a phosphor, because we know, like over the past few decades, for perovskites, especially the lead-based perovskite, has shown greater potential toward for application in optoelectronic materials, and it has achieved a large amount of breakthrough in photovoltaics, and now it's competing with the traditional silicon solar cells. And due to this exciting optoelectronic properties, nowadays like researchers are implementing lead-based perovskite in different lighting applications, from LED to laser to some display materials, as well as in photodetectors. So why perovskite, like lead-based perovskite, show these properties? So first, it gives a better charge transport. It has a very good defect tolerance ability, and also it gives some like intense optical transition, and its band gap can be tuned for achieving our desired emission, and finally, its fabrication is very easy as compared to other phosphors. As I told, like perovskites are now widely studied as a phosphor. So here you can see like the research in the research, like researchers are already implementing nanocrystals and studying its properties for perovskite based display. And also in some company they are like making some fabrication line where they are planning to implement like perovskite quantum dot as a phosphor material. So if we like talk about the challenges that phosphors face today, is first of all its complex fabrication. As we have seen those general phosphor materials, their fabrications are very much challenging, and they can be done through various like vacuum or high temperature processes. However, like perovskite based phosphors overcome the first challenge, but in case of perovskite, the lead based perovskite, the lead is a problem because it has some toxic effect on the human health as well as environment too. And the perovskite which are being developed as a phosphor, they also show some issue with the stability towards the outer environment. It requires intense research to overcome these challenges. When we look into the replacement of lead in the perovskite based phosphors, so already researchers had tried replacing lead with the elements which share the similar row and column with lead, and in that case the optoelectronic properties achieved from those perovskites are not similar to the lead based perovskites, and also they form the lower dimensional material. So that is like that is a drawback for the lead free for those lead free perovskite. So now it is a high time to search for some luminescent material, for some elements that show some luminescent properties, and among for that the transition elements are widely studied because this transition element shows a good amount of luminescence. And among those transition element, manganese, copper and zinc are widely studied. Even like in some like regular phosphors, these transition elements are used as a dopant to increase their luminescent properties. So when we think about like replacing lead with manganese, so what are the advantages it gives? First of all, it is like manganese is an earth abundant element and it's environment friendly. It gives a high luminescence because manganese itself has some luminescence property. Then its like band gap can be tuned, and due to that, like it gives a tunable emission, and it also shows a pure band emission. So if we look into the perovskite structure or the manganese-based phosphor structures, so we can see it forms two derivatives. First is CS3MnBr5, which is a 0D structure, and it shows green emission. The other derivative is the CSMnBr3, which is a 1D structure. It forms a hexagonal 1D structure and it gives red emission. And the advantage of this perovskite over the lead-based perovskite is this is a non-toxic variant, and it shows a high PLQI, and also it gives a good carrier mobility. So this material can be used as a lead-free optoelectronic material. So with this keeping in mind, we set our research goal for the synthesis of manganese-based phosphor, and like this is manganese-based perovskite phosphor with a easy fabrication approach and a like green and cost-effective synthesis method. So as reported in the previous papers, the researchers who has fabricated the CSMnBr based phosphor, they had either used hydrothermal method or anti-solvent method or hot injection method. So these methods are like cheaper and easier. However, they use like some toxic organic inorganic solvent anti-solvent, and the vapor of those like solvent anti-solvents create health issues for the researchers as well as it is toxic for the environment. So how you can like improve this situation. Just we have to change the solvent or the anti-solvent to some greener option. And secondly, when we check like CSBR and MNBR are soluble in water, so why not give water a chance as a solvent? So what is the importance of water? We know, like in a general perspective of view, water is a source of our life. It maintains our ecosystem, helps in growing our food and agriculture, and also in development of our socio-economic systems. And when we see it in a researcher perspective of view, so water is a combination of two hydrogen and one oxygen atom, and it is a green solvent. Like most of the salts are precursor salts are easily dissolved in water, and finally the byproducts that are produced by water is we can easily drain it. So or else we can say there is no byproducts. When we checked the use of water in the perovskite research, and as we know, like these perovskite materials are very much sensitive towards humidity, so we checked like whether water can be used as in synthesis of perovskite or not. So recently we found some researchers has published the use of water in the synthesis of lead based perovskite, and also they had used water in the synthesis of non-lead based perovskite. So based on that, we developed a research module in our lab, or a research method in our lab, where we had synthesized those phosphor materials using um, the water only. And from the phosphorus material that we had achieved from our experiment, those had shown very high PLQI and has been used in some UV pumped LED applications, as well as it has shown some good photo response and has been used as a photodetector too. So what is our approach? So in our approach, we just simply mix the precursors into water, and we just mix it for a certain period of time under a particular environment, and then we just filter the solution, and then we freeze dry the solution to form ice. Finally, we just do the lyophilization, and through this lyophilization process, those water molecules are removed from those freezed solution, and as a final product, we achieve those phosphors. So, what is the advantages? This gives easy water-based synthesis method, which is non-toxic, cost-effective, and the best part is we can produce a large quantity of phosphor in a single go. When we check the material properties of our synthesized phosphor, so we can see like a 0D structure has been formed in case of CS3MnBr5, and when you check the ADAX, we can see the atomic percentages are almost similar with matching with the stoichiometry of the material. The similar thing happened in case of CSMnBr3. We achieved a 1D structure, a hexagonal 1D structure, and in this case the atomic percentages are almost similar to the stoichiometry of the material. So for further confirmation, we did the XRD of our material, and when we matched our XRD with their standard counterparts, we can see the peaks are well matched, and from this we can confirm that okay, our material is forming. So next we check the material properties of our phosphor, because this is very much important for any material to be declared as a phosphor. So in case of CS3MnBr5, we saw a bright green emission, and in case of CSMnBr3, we had seen a red emission, as reported from the previous researchers, as reported by previous researchers. So to understand why these properties are coming, so when we checked into CS3MnBr5, so it shows a good excitation range in the UV as well as in the blue region, and shows a green emission. So this can be explained by the emission from the free manganese ion, and this is where we can see it easily absorbs the UV and the blue range emission, and emits in the green emission. And when we check for the CSMnBr3, So here the manganese quantity is high. So due to that, the excess manganese population, the interaction between the manganese ion split this energy level to many sub levels. So due to that, the CSMnBr3 absorb these high energies, and after a certain non-radiative transition, they emit with red emission. So due to that factor also, we can see the PL decay time for CSMnBr3 is high, because in this case we had seen a higher non-radiative decay, and in case of CS3MnBr5 the PL decay is less. So based on those interesting optoelectronic properties, what we did is we fabricated, or we designed a UV pumped LED. So in that case, what we used is like 365 nanometer UV chip, and on that we had placed our CSMnBr3 and CS3MnBr5 individually, mixing with some optical adhesive. So when we plotted our luminescence value that we had achieved from the LEDs, we can see a bright green emission from CSTM-NBR5, and with the increase in the voltage, we can see this emission level has increased. And similarly, in case of CSMnBr3, we had achieved some red emission, and also in this case, with the increase in the voltage, the emission limit has increased. And based on our research, now we are focusing on fabricating the micro LED with our CSMnBr material, and also we are trying to develop some inkjet method for like printed LED displays. So on a conclusion note, we had developed a simple method for synthesis of manganese-based perovskite phosphors, and this variation, just with the variation in the precursors, we had easily achieved like green and red emission. The green emission arises from the individual Mn2 plus ion, whereas in case of CSMnBr3, the excess of ion split the energy levels, and due to that, we can see some low energy emission, that is the red emission. And in both case of the phosphors, it is implemented as a UV chip for the fabrication of a UV pumped LED, and in both the cases it has like shown promising results. So we can conclude like our work would be a new way, or would give a new pathway or new strategy for designing or fabricating the optoelectronic phosphor based material or phosphor based device. So here is our team, and we work together on different energy based materials and phosphor based materials for various applications. So thank you very much.